Hello everyone, my name is Batu and I am an embedded software engineer. I am working at the intersection of real-time embedded software and machine learning. Specifically, I deploy inference on edge hardware that is constrained by memory, computational power, energy consumption, and deterministic timing. This video completes a project I call Edge AI across the compute spectrum. The objective was to deploy the same machine learning workload across three distinct classes of hardware, from the most resource constrained to the least, and measure how latency, throughput, and power efficiency shift across that spectrum. Tier 1 was a microcontroller, an STM32F407 running FreeRTOS, where I trained a small neural network to classify human activity recognition data into 6 classes, then I quantized it and deployed it. Tier 2 was an embedded GPU board, the NVIDIA Jetson Nano. Both videos are linked in the description. This video is covering Tier 3, a laptop-class Apple Silicon chip, the M5 Pro. As this video references the first two videos throughout and also includes a cross-tier comparison of the results, I strongly recommend watching the series from the beginning. Tier 3 differs from the two before it in one specific way. The STM32 only has a CPU. The Jetson has a CPU and a GPU. The M5 Pro chip has a CPU, a GPU, and a third unit which is the Apple Neural Engine, built specifically for machine learning inference. So this tier asks a narrower question than the previous ones. When a platform offers several kinds of accelerator, does a small model benefit from any of them? And if not, how much work does a call have to carry before each one starts to pay off? When we look at what this video covers, the work is divided into 6 sections. Section 1 ports the human activity recognition model from Tier 1 onto the platform. Section 2 compares CPU against GPU at a single sample per call, which is the batch size this application uses in deployment. Section 3 sweeps batch size upward to find where the GPU overtakes the CPU. Section 4 tests whether the neural engine is used at all. Section 5 measures power draw on both execution paths. And Section 6 places all three tiers side by side, which brings the whole series to its conclusion. The M5 Pro is a system on chip with a unified memory architecture, the same arrangement as the Jetson in Tier 2. The CPU, GPU, and neural engine share one physical memory pool rather than communicating across a PCI Express link. This removes the explicit host-to-device copy that consumed roughly a third of the end-to-end path in Tier 2, but it does not remove the cost of dispatching work. The CPU has 18 cores, 6 of what Apple calls supercores and 12 performance cores. Memory is 24 GB, unified across all three compute units. The GPU is reached through Metal Performance Shaders, Apple's GPU compute framework, and the neural engine through Core ML. The machine runs macOS Tahoe 26.5.1, and exact software versions are visible on screen. Section 1 is a prerequisite rather than a measurement. The premise of the series is that all three tiers run the same classifier, so before anything is timed, the model has to arrive on this platform intact. The model is the Human Activity Recognition classifier from Tier 1. It takes 561 features derived from accelerometer and gyroscope data and predicts one of 6 activity classes through 3 fully connected layers and 38,246 trainable parameters. It is the small dense network that I already deployed on both the STM32 and NVIDIA Jetson Nano. It was originally trained in Keras, however reaching the Apple GPU requires PyTorch, because PyTorch's Metal Performance Shaders backend is the supported path to the hardware and Keras does not provide an equivalent. So an identical architecture was constructed in PyTorch and the weights were transferred layer by layer. This script also verifies that this transfer was successful. The same input was passed through both models and the outputs were compared. The maximum element-wise difference was 0. The network benchmarked in the rest of this video is therefore numerically the same network that was initially created in Tier 1. Section 2 asks the most direct question available. Does the GPU help at the batch size this application actually uses? Human activity recognition operates on a sliding window of sensor data, producing one feature vector per window, so the deployed batch size is 1. One reading in, one prediction out. Each configuration was measured over 1000 timed calls after 50 warm-up calls. The GPU measurements required one precaution. Metal dispatch is asynchronous, so each GPU timing is followed by an explicit synchronized call. Otherwise, the measurement would report queuing time rather than completion time. The CPU completed a forward pass in 0.0114 milliseconds, whereas the GPU required 0.0740 milliseconds. The GPU is therefore approximately 6.5 times slower. The explanation is dispatch overhead. Before the GPU performs any arithmetic, the CPU must encode the command, submit it to a queue, and synchronize on the result. This forward pass is three matrix vector products totaling 38,144 multiply accumulate operations, which a single CPU core completes in a few microseconds. The fixed cost of engaging the GPU exceeds the cost of the computation being dispatched. This is the same conclusion Tier 2 reached on different hardware through a different toolchain, where TensorRT on the Jetson showed no measurable GPU advantage on this model. Two vendors' accelerators independently produced the same answer about this workload. Here, it is useful to mention this one note on parallelism. Neither backend here was handwritten. PyTorch distributes the layers across CPU cores through its OpenMP-backed A10 backend, and moving the tensors to the metal device delegates kernel selection to the framework. Section 2 establishes that the GPU loses, but not why. Is this GPU poorly suited to this network, or is a single sample simply too little work to justify dispatching it? Section 3 separates the two. Those two explanations behave differently as work per call increases. If the GPU were structurally unsuited to this network, a larger workload would not help. If dispatch overhead is the constraint, giving each call more work to amortize it should progressively close the gap. Batch size here means the number of input samples processed in a single call. The sweep ran batch sizes of 1, 8, 32, 128, 512, and 1024, with 200 timed calls at each point on both devices. At batch size 1, the GPU delivered 14% of CPU throughput. At 128, 81%. At 512, it passed the CPU for the first time at 1.27 times. And at 1024, it reached 2.31 times the CPU. The deficit narrows monotonically as batch size grows, which rules out a structural mismatch and confirms dispatched overhead as the constraint. The behavior after the crossover is more informative than the crossover itself. Between batch 512 and 1024, CPU throughput increased by approximately 17%, while GPU throughput increased by 113%. The CPU is approaching saturation with no additional cores to bring to bear. The GPU is still filling and had not reached its own limit at the largest batch size tested. So 2.31 times is a lower bound rather than a peak, and the sweep terminated because of the range I selected, not because the hardware stopped improving. One qualification: a batch of 1024 means 1024 sensor readings arriving simultaneously, which a streaming workload does not produce. This measures what the silicon is capable of, not what this application would request of it. Its value is in locating the boundary. Taken together, sections 2 and 3 establish the central result of the sphere. On identical hardware, the same GPU is 6.5 times slower than the CPU at 1 sample per call and 2.31 times faster at 1024. The constraint is the size of the workload, not the capability of the hardware. Section 4 applies the same question to the one remaining compute unit. Section 4 addresses the Apple Neural Engine, the compute unit designed specifically for inference and therefore the one most likely to help. It cannot be reached from PyTorch. Access is available only through CoreML, so the model required conversion. Direct conversion from Keras also failed, and the path that succeeded routes through PyTorch and a traced graph, which is why the pipeline retains a PyTorch stage that would otherwise look redundant. CoreML also does not behave the way the API initially suggests. It does not accept an instruction specifying which compute unit to use. It accepts a permission, and its own scheduler decides what to use within whatever it has been allowed. So this measurement reports what the scheduler chose, not what was requested. CPU only measured 0.0341 milliseconds. CPU and GPU measured 0.0337. All units, including the neural engine, measured 0.0341. All three are indistinguishable within run-to-run variation, consistent with the idea that the scheduler having executed the model on the CPU in every case. So latency alone cannot establish that. Identical timings would also result if the neural engine had executed the model and happened to match CPU performance exactly. The two hypotheses are indistinguishable from timing data. The power measurement in the upcoming section resolves it. Across every sample of every run, including the runs in which the neural engine was explicitly permitted, its power rail reported 0 milliwatts. A compute unit drawing no power is definitely not executing work. Two independent signals, latency and power draw, agree that the accelerator was available and the scheduler declined to use it. The most likely explanation is the one established in the previous two sections. The neural engine is designed around large convolutional and transformer workloads, and engaging it carries a fixed cost that a three-layer network of 38,000 parameters does not repay. Apple's scheduler applies a cost model that reaches the same conclusion the GPU measurements reached independently. Section 5 measures energy rather than speed, since this determines whether any of the preceding throughput figures will be affordable on a platform operating from a battery. Power was sampled with power metrics at 1 second intervals concurrently with the benchmark. It reports the CPU, GPU, and neural engine rails separately, which is what made the confirmation in the previous section possible. At idle, the machine drew 298 milliwatts across the three rails. During CPU execution, that rose to approximately 2.5 watts. During large batch GPU execution, approximately 8.6 watts. The distribution across those rails during GPU execution is the result I did not expect. The GPU rail rose to 273 milliwatts, while the CPU rail rose to 8,284. The CPU therefore accounted for approximately 97% of the power drawn during the work that is nominally executing on the GPU. My explanation is that on a unified memory architecture, the CPU does not go idle while the GPU computes. It encodes commands, submits them, synchronizes on results, and manages memory throughout. In a benchmark loop submitting calls back to back with no other work in between, that overhead becomes the dominant power cost. Dividing throughput by combined power yields approximately 35,600 inferences per second per watt on the CPU at batch size 1 and approximately 1,515,000 on the GPU at batch size 1024. Tier 3 is now complete. Before moving on to the comparison across all three tiers, I would like to note that this tier's full scope and limitations, covering timing rigor and measurement precision, are documented in the GitHub repository. That is linked in the description. To summarize this tier, the model was ported with exact numerical equivalence. The GPU proved 6.5 times slower than the CPU at a single sample per call, then overtook it at batch 512 and reached 2.31 times by 1024. Therefore, the workload rather than the hardware was identified as the constraint. The neural engine was never engaged by CoreML's scheduler at any setting. This is confirmed independently by a zero reading on its power rail. The CPU accounted for 97% of power draw during nominally GPU work. Across every measurement, this chip's specialized silicon offered no benefit that a workload this small could actually reach. Section 6 places all three tiers side by side, which is the objective the whole project was constructed to reach. Latency and throughput rank as expected. Single sample latency falls from 0.787 milliseconds on the STM32 to 0.045 on the Jetson to 0.014 on the M5 Pro CPU. Peak observed throughput rises from approximately 1,300 inferences per second to 16.3 thousand to 88.6 thousand on the CPU and to nearly 13 million on the GPU at large batch. Energy efficiency in inferences per second per watt does not rank the same way, and this corrected an assumption I held before measuring it. The STM32 and Jetson swap places. The Jetson beats the STM32 on raw throughput but falls behind it on efficiency. The M5 Pro still leads on both. Its CPU delivers 3.7 times more inferences per watt than the microcontroller, and its GPU at large batch approximately 157 times more. Newer silicon, built on a more advanced manufacturing process, performs more work per joule, and architectural simplicity does not compensate for that. What the STM32 wins is absolute power, approximately 132 milliwatts against 2.5 watts. That is a deployment gate rather than a performance ranking. If a platform's power budget is 200 milliwatts, the laptop chip is unavailable, regardless of how efficiently it converts watts into inferences. Efficiency only becomes the deciding metric once the absolute draw is affordable at all, and for a battery-powered sensor node, it frequently is not. The Jetson is the weakest fit for this particular workload. It ranks last on efficiency and draws 6.9 watts to deliver throughput the M5 Pro CPU exceeds 5 times over at roughly a third of the power. That is not a deficiency of the board. Tier 2 measured the same Jetson reaching 266 times a single-threaded CPU baseline on a handwritten QDAM matrix multiplication. The hardware is capable, but this model is too small to occupy it. There are two conclusions. One of them is specific to this workload, and the other is more general. For human activity recognition, the answer is clear. The UCI Human Activity Recognition dataset classifies a 2.5-second window, so a deployed system requires roughly 1 inference per second, while the STM32 delivers 1,300 per second at 0.79% CPU utilization on approximately 132 milliwatts. It exceeds the requirement by more than 3 orders of magnitude on the smallest platform in the series, so nothing about the microcontroller is really justified for this workload. And the useful question is not which platform is fastest, but how much of the microcontroller remains available for everything else the device has to do. And at 0.79% utilization, nearly all of it is still available. The general conclusion is the pattern that repeated across all three tiers. On the STM32, the classifier ran at under 1% CPU utilization. On the Jetson, it showed no measurable GPU advantage and no benefit from reduced precision. On the M5 Pro, the GPU lost outright at batch size 1 and the neural engine never engaged at all. 3 platforms, 3 toolchains, 3 vendors, and the same answer each time. Accelerators only pay off when a single call carries enough arithmetic to cover the cost of dispatching it. This classifier performs 38,000 multiply accumulate operations per inference, while MobileNet V2, which ran on the Jetson GPU in Tier 2 without any timing instability, performs roughly 300 million. The threshold sits somewhere between those two figures and was not measured in this project. Below it, the CPU wins on every platform I tested, and the specialized silicon remains idle. Section 3 demonstrates the other road past that threshold. Aggregating enough small calls into a single batch also clears it, which is why the M5 Pro GPU overtakes its own CPU at batch 512, but that option is available only to applications that can afford to wait while the samples accumulate, and a streaming sensor workload cannot. A vision model processing many camera frames per second, or a batch job classifying a stored dataset overnight is the kind of workload that would actually justify using the Jetson or the M5 Pro over a microcontroller. That completes Edge AI across the Compute Spectrum project. The whole project is on my GitHub. If you have any questions or suggestions, you can always reach me through my LinkedIn or email. I would like to hear if you have any comments or any ideas for future projects as well. Thanks for watching.